during module 3. So again, there's 5 modules. The first module we learned about communicating structure through bonding patterns with the elements of the periodic table, how they form functional groups. Then in module 2, we learned how the spectroscopic techniques allow us to determine if those functional groups are in a molecule. And now we're going to dive one layer deeper into Dante's hell here and look at physical organic chemistry, which is going to allow us to rationally predict where in a molecule a reaction will happen. And so the first big part of this is reviewing acid-base chemistry. And so we covered that in Gen Chem, but as we'll see today, there's really sort of 2 classes. There's strong acids and bases, and then there's weak acids and bases. The functional groups that you've learned so far are primarily weak acids. So that's the difference between Gen Chem and now. And basically, we're going to learn how to rank the functional groups according to acidity. And based on that ranking, you can predict where a reaction will happen. And so that's what we're trying to, ultimately develop an intuition for. Is not, the products can be whatever. We want to say the products are going to be this exact. And so part of that lump of module 3, we start with alkanes and cycloalkanes. And then we'll move into something called conformational analysis. And that is also important in predicting reactivity because sort of the way we draw things, you can draw like the same molecule a couple different ways. But in reality, the molecules will achieve sort of their natural ground state. But then they may have to move or do bond rotations to get into a reactive state. And once we start introducing that, then we'll start talking about mechanisms. So you have starting material, reagents, they go to products. But then what we want to understand is the pathway to get there. How does that happen? And so this is a pretty crucial module as well, again, because we want to be confident in predicting the products. We don't want to be lost and say they can be whatever. We want to be, it's going to react here because of this, that, or the other principle. So any questions before we get started? Your exam 2B grades are, you can see the sheets and zip grade with pictures of what you got right, what you got wrong. Your scores are posted in Canvas. Your grades have now been posted in SOAR. And I don't know, you might only get access to them on Monday. Is that? So you'll see your interim grades. So 77% of the population of 140 is getting A, and then the rest are getting B's, C's, and D's. So again, hopefully that's clear on the little announcement in Canvas about how things are going to go. But it looks pretty positive, I would say, in terms of a trajectory and finishing off the semester, earning the grade that you want to earn. Again, if you've made mistakes on the exam and you want to review that, the best thing to do is just get a sheet of paper, go through the ones you got wrong, think about what you did wrong, write out a little explanation, and if you want to come see me, you can review that. But that's how the exams will look from here on out. And the 2-column format. How many people took Gen Chem here at USM? So you're familiar with the ACS exams, so that's how your final exam will work. They're a little bit more restrictive on things for the final, no calculator, that sort of thing. So you have to be comfortable doing that sort of simple math in your head when that comes around. But for the 12 or so chapters we covered, the final exam has 70 questions. So about 2 to 3 questions per chapter in terms of the weight of
that material over the whole semester. So what is new? The first couple bullet points show the skills that you should be comfortable with moving forward. And really what's new is now that you know the functional groups, we want to put a number to them. And that number is called the pKa value, and that deals with acidity. That's how we rank the reactivity in the molecule. So determining acidity of hydrogens, which hydrogen's going to react first. And then we'll get into, conformational analysis, how the bonds rotate, what's important for that in terms of mechanisms. And then stereochemistry is probably something new. We'll talk about when a carbon atom has 4 different substituents in space, you can arrange those things 2 different ways. So there's a nomenclature set of rules for determining that. And so this word isomer, we're going to expand it out a little bit more. There's a lot of isomers in organic chemistry. You're familiar with constitutional isomers. And then the next thing we'll talk about is stereoisomers near the end of this module. So we'll spend some time here reviewing just some concepts and words from Gen Chem. In terms of acids and bases, is sulfuric acid, H2SO4, a strong or weak acid? So that's a strong acid. And again, as we communicate names or reagents of things, so there's the sulfuric acid. And in your brain, you should be thinking of a molecular formula. It's H2SO4. And then the next thing is convert that to a Lewis structure. So sulfur on our periodic table, sulfur is below oxygen. So that's like period 3 moving across. So it has access to d orbitals. So far we've only talked about s and p. There are 5 d orbitals, and because sulfur can use them, it can expand its octet, and we see that in sulfuric acid. So sulfuric acid is a strong acid. There's the structure. And when we talk about acidity, sulfuric acid is diprotic or diacidic because there's 2 H's that can be removed. So if you remember down into the nitty-gritty of doing acid-base titrations, remember what those curves look like? Sort of like an S curve. So sulfuric acid has 2 points at which you reach equivalence when you're titrating with a base. You deprotonate the one, you add more base, and then you deprotonate the other. So we'll talk about the mechanism for deprotonation, the charges that are then involved, and how we must balance those charges. So acetic acid, that's a common name. The 2-carbon unit is basically called an acetate derivative. The IUPAC name would be ethanoic acid. But its structure is this. So that's the acid that's in vinegar. So if you have vinegar at home, that's the acid. If you can sort of synthesize in your mind what vinegar smells like, that's what straight acetic acid smells like. It's pretty potent. You can eat it. It's an Italian dressing. So, the oil and water, the acetic acid's in there to give it that tang. So is this one strong or weak? So this is a weak acid. And the point that I'm trying to make here to you between acetic acid and sulfuric acid, they both have OH. So if they're both OH, what makes one different from the other? And so it's the rest of the molecule that influences the acidity. And that's what we want to understand, are these factors that change acidity moving from one functional group to the next. So the sulfuric acid will be stronger. And so the definition of an acid is it's a proton donor. And a base is a proton acceptor. So again, if they both have OH, that little part of the molecule that's donating the H, if the OH is common, why is one so much stronger than the other? And as we'll see, it's the other elements in the functional group in the molecule that change the strength of the acid. So again, here you see OH and OH. The H in the H are what is being donated. Or put another way, the base is abstracting that hydrogen. And so we'll look at how, this rest of the molecule in sulfuric acid versus this rest of the molecule in acetic acid influence that acidity value. And I mentioned that we want to be rational in how we go about determining where a reaction is going to take place. So if we look at acetic acid, how many unique sets of hydrogen does it have? So it has 2 unique sets, and then the ratio is 3:1. So the question to you is, if you took that molecule, and I'm just going to say B for base, so the base has a lone pair that's going to abstract the hydrogen. If you have 2 sets of hydrogens, how do you know which hydrogen is going to be abstracted? And so that's going to be what we want to understand. Even though we're calling it acetic acid, that's the most acidic proton. But again, you have this other set here, the methyl group. Why doesn't the base abstract a hydrogen from the methyl group? Why does it go after the OH? And so as we learn, the scale of acidity called pKa, we'll learn how to match appropriate bases to the pKa values so that we know a reaction will happen. So there's the 2 unique sets in the ratio of 3:1. So the 3 is from the methyl group. The 1 is from the OH group. So if we were treating with sodium hydroxide as a base, so Na plus OH minus, what unique set will react first? And then how do we determine that? So this is the most acidic hydrogen, so that will be abstracted. And then we get two products from that. We get sodium acetate and then water. So for every acid-base reaction, you have the acid-base starting material, and then you're ending up with two products. Notice the negative charge from the hydroxide oxygen now migrates over here, so that's negative. The sodium is what we call just like a spectator ion. That plus charge balances out the negative, so everything ends up neutral. So we have to keep that in mind as we look at these reactions. We can't form an excess of negative or positive charge. Things have to be balanced. So we've gone from acetic acid now to these two molecules, which are a little bit more complex, I think you would agree. And what's the issue? So gifritoxin was the alkaloid that was isolated from the skin of those little frogs. And apixaban, drawing a blank on what it's used for, I think it's either low blood pressure or like smoking cessation. But the question to you is, knowing everything that you know, how many unique sets of hydrogen are there? And then if you were to treat these molecules with just one equivalent of a base, where would that base react? And so to help guide us do that, the first thing we would do is identify the main functional groups. So for example, this is a terminal alkyne, cis alkene, tertiary amine, primary alcohol, and then everything else along the backbone here that I'm sort of walking along, that's your CsP3 hybridized carbon H bonds. In apixaban, we have a tertiary amide, a benzene ring, another tertiary amide, primary amide, aromatic ring, ether, and then you have your sp3 hybridized CH bonds. So the question is, again, where is a reaction going to take place? And we don't want to feel overwhelmed about just throwing like a dart at the board and say, okay, it's there, because then we have no rational reason for saying that. So to put all of this into context, today's lecture will primarily focus on the review of acids and bases from a general chemistry point of view, where we're looking at sort of strong acids. Then on Monday, we're going to start with weak acids, which are all the functional groups that we've learned already. So we'll circle back to water, H2O, and that's the universal solvent on Earth. The molecular weight, 18 grams per mole. It freezes, melts at 0 degrees Celsius, and boils and condenses at 100 degrees Celsius. So to understand the concept of acidity, we'll just review water. And even though water is sort of simple H2O, it's chemically complex. I mean, people still study water for a living. So not everything is known about it. So water will undergo what's called autoionization. This just happens, like at any temperature. And that's basically where you see you have a neutral molecule, and then it's forming these ions. So that's just called a proton, H+, and OH- is called hydroxide. So you see you have plus, minus. Overall, they balance, so it's neutral. So auto means it just sort of happens, and then ions are forming these two ions, and the charge is balanced. Probably some of your darkest days in general chemistry were learning about setting up these equations here for equilibrium, and then doing the ice tables. You remember that? So an equilibrium expression is when you look at the products and we put them in form of concentration, and then you divide that by the reactants. So the concentration of the proton times the concentration of hydroxide divided by the concentration of water. And it's been determined that pure water has a concentration of 55 molar. So really that's a constant, and what happens, it gets folded back into this K value. So what is the term molarity, M? What units does that have? So moles per liter. And again, that's what the square bracket means. So if you see something in the square bracket, the unit is molarity, moles per liter. The other ones are used in Gen Chem, they're used in analytical, but they're kind of a pain in the butt to deal with, right? Moles per kilogram, kilograms per liter, that's sort of like density, and equivalence. What does equivalence mean? So if I say H2SO4, we can think of that as two equivalents of proton. Like acetic acid, CH3, CO2H, that would be one equivalent. When we're talking about that acidic OH group. So that's kind of what equivalence means. Again, that's also used in titration terminology when you reach the equivalency point. And we'll see that in the next couple slides when we talk really qualitatively about the pH scale, whether something's acidic, neutral, or basic. So here again is the equilibrium expression K. That 55 molar gets, shoved into the K term because it's a constant. And so essentially, K of water, we call that KW, is equal to those two concentrations, and then it's set to 1 times 10 to the negative 14. So that should sort of be familiar to you from acid-base chemistry and the pH scale. So the 14 is sort of our bracket for pH. So if you have a aqueous solution and the concentration of proton equals the concentration of hydroxide, how would you describe that system? So that would be neutral. You don't have an excess of one over the other. They're exactly equal, so it's neutral. If the concentration of proton is greater than hydroxide, how is that described? So that's acidic. And the other situation, I don't have a slide for it, but if the concentration of proton is less than hydroxide, that's basic. And so that's summarized here using that KW relationship. And really, even though we're using these letters here for these species, if you were in the lab doing this, you would shove some numbers in there, and then you would get, an outcome of that number. So if proton is greater, it's acidic. If they're equal, it's neutral, and if proton's less, it's basic. So from Gen Chem, you probably learned about 3 different theories of acidity. And as we'll see in the table here, they range from pretty specific to very general. And so there's the Arrhenius theory, Bronsted-Lowry, and then the Lewis theories. And really what they're talking about is sort of the species involved. The Arrhenius theory only deals with proton and hydroxide. The scope of that is pretty narrow when you think of all the acids and bases there are. So Arrhenius, it's limited in what sort of chemicals fall under that category. Bronsted-Lowry is more general, and so this is what is typically used for organic chemistry. We say that an acid donates H+, which is a proton. And now look at the difference between Arrhenius and Bronsted here for the base. We say a Bronsted base accepts H+. So we've moved away from hydroxide, and we've generalized it a little bit more so that the base can be anything that will deprotonate H. The most encompassing theory is the Lewis acid-base theory, where we're not talking about proton or hydroxide anymore. We're talking about the movement of electrons. And again, that relates to the mechanisms. So a Lewis acid accepts a pair of electrons. A Lewis base donates them. And what you'll find if you think of the Lewis definition, it jives with Bronsted and Arrhenius once you start seeing how they compare. So Lewis is, again, the most general, and any other theory will fall under it. So let's look at this straightforward reaction where you take hydrochloric acid and water to generate hydronium ion plus chloride. So I'll write some things on this slide, and then the next run of slides is sort of the individual questions. You see in the name there that says acid. And if we're talking about acid-base reactions, water has to be a base. So I'm going to put the lone pairs of electrons on water. And then if you look at the product side, you see hydronium ion. So it has an extra hydrogen on it. So that hydrogen had to come from the hydrochloric acid. So how does it happen? In terms of the Lewis base theory, the acid HCl is going to accept a lone pair of electrons from water. Water is the base, is going to donate that lone pair. And the way we show that is using what's called curved arrows. In this sense, the arrow will start from that lone pair and it's going to point to that hydrogen. So the arrow is showing you that lone pair is going to abstract that H. In terms of writing a mechanism, we're forming an OH bond. We still want to obey the Lewis dot structure, so now we have to break another bond. And so the next arrow will start between the H and the Cl. And then the chlorine is going to get the electrons in that bond. So we form hydronium, we form chloride. The plus is equally balanced by the minus, so overall they're neutral. So there's your acid, there's your base on the starting material side. Then on the product side, we also have an acid-base pair, but these are now called the conjugate acid, conjugate base. So on the product side, hydronium is the conjugate acid. And chloride ion is the conjugate base. So one thing you need to be able to identify are these conjugate acid-base pairs. So the thing that started as the base will end up as the conjugate acid. The acid ends up as the conjugate base. And again, does that make sense? When we look at chloride and we put in the lone pairs, those four lone pairs, again, that is a Lewis base because now it's an electron pair donor. It can abstract a hydrogen, so it sits in with the Bronsted definition as well. So the water, again, is the base. Hydrochloric acid is the acid. The conjugate base here is the chloride ion. Again, that's due to the lone pairs. So that acid becomes that conjugate base. And then hydronium is the conjugate acid. From water being the base. So it says, so how does hydronium ion form? And as I said, starting materials go to products. The how is the mechanism. How are the electrons moving to form bonds and break bonds? And that process, again, is all restricted to what you learned about Lewis dot structures. The neutral bonding patterns, or if they're not in that, how do you assign plus or minus charges? So you still are under that regime where you can't violate any of those rules. So the curved arrow formalism, how electrons move. So typically they'll start at a lone pair, or they'll start at a pi bond, or if you're breaking a bond, they'll start at a sigma bond. And notice the arrowhead here. That has to point at an atom that can reasonably accept those electrons. And that, again, is dictated by electronegativity. So really what we're talking about is matching polarity. You don't really want, an arrow pointing to something that's already negative. Because if you think about like magnets, they'll repel one another. It's the same sort of concept. So we would call the start, the source, in there where it ends up, the sink. The source and the sink in describing the movement. So let me just write on here, make and break. So we're making an OH bond and we're breaking an HCl bond. And when we get into module 4, that's when we'll start looking at what's called bond dissociation energies. And that's going to further guide us in helping to predict what is favorable and what's not favorable. We'll actually look at the energy required to make an OH bond and the energy required to break an HCl bond. We'll do some simple addition, subtraction to see, okay, is this favorable to go towards the products? Or if the reagents are not matched, the energy is too great, it just won't happen. They won't react at all. So, this is just a gradual introduction to this arrow pushing, but that's the logic that organic chemists use to help keep track of the flow of electrons, to actually say, okay, we formed this stuff and this is how we think it's happening. So let's look a little bit more at water. Even though it's a pretty simple structure, H2O, it's pretty complex. And again, today we're focusing on strong acids, which primarily deal with water. When we get to Monday's lecture, because this is organic chemistry, reactions are not really run in water. They're run in organic solvents. So now we have other things to consider at this sort of line between strong and weak. Water is known as a leveling solvent. And simply what that means is, if you look at this structure here, HA, this is going to be sort of any acid. H is the proton, and then A is the rest of the molecule. If you take a strong acid, HA, and you dissolve it in water, it will always form hydronium. And then the other thing that you get left over is that conjugate base, A minus. That's the anion that balances out the plus charge of hydronium. So water plus any acid is going to give you hydronium plus that conjugate base. And acid-base theories, they can get pretty complex. One thing I want to emphasize to you that's sort of different from Gen Chem, these reactions are not based on concentration. That number molarity in square brackets. You can think of an acid as being very concentrated, but that is not related to which side of the arrow is preferred. The term acidity is better described as the extent at which those things ionize. And so another word that's used is called activity. And we don't talk too much about that in here, but in analytical chemistry, you'll learn more about it. And if you take physical chemistry, that's when you'll learn the nitty-gritty math of it, which is a little bit scary. Because then you're dealing with like integrals and derivatives and stuff like that. But so just keep in mind, we're not talking about concentration as a translation to acid-base strength. When we talk about strength, it's the extent at which these things ionize. So now that we're getting away from just sort of a restrictive definition of an acid, we're going to generalize the equilibrium expression for pretty much any acid we deal with, HA. So the acidity constant Ka, we do the same thing. The concentration of hydronium times the concentration of that anion, now divided by the concentration of the acid. And so that's the Ka value. If you remember, Avogadro's constant, Avogadro's number, it's pretty big, right? 6.02 times 10 to the 23. And so when we're talking about these numbers for this equation, those numbers can be like really huge or really small. And for humans, that's kind of tough to compare things when you have big numbers and small numbers. So a mathematical function is then applied to this equation. And we just call it like a p function. And that deals with logarithms. So to set the stage for that, let's just do a little bit of qualitative reasoning here. So there's the equation we're going to use. Now what we want to think about, if the number for hydronium is much greater than HA, what's the result overall for Ka? For example, you can plug any number you want here. If you say hydronium is 1,000, HA is 1, that's going to give you a big number. So we would say it's D, you get a large number. Again, we don't have to put in like specific things. We're just trying to come up with a general concept of how these concentrations overall affect Ka. In the second scenario, if hydronium is 1, HA is 1,000, 1 divided by 1,000 is a small number. So that's A. And again, this is the equation that's used when you stick like a pH meter in your solution and you're titrating. You get the numbers and then you would shove them in this equation, and that's ultimately what falls out of it. So in terms of the scenarios we just looked at, we plug these numbers in to determine if hydronium is greater than acid. We said that was a large number. Hydronium is less, that gives us a small number. And then how does that translate chemically into the equation? So when I say equilibrium, equilibrium is a weird word, even though it has sort of like the word equal in it. That does not mean 50% starting material, 50% product. It means at some point in time, there is going to be a ratio set up of the starting materials to the products. That ratio does not and generally will not be 1-to-1. So if the equilibrium is set up, you have more of the hydronium, that means the equilibrium favors the products. So the arrow is shown more to the right. And then we would say, okay, that's a strong acid because most of it is ionized to hydronium. If at some point in time the hydronium ion concentration is small, the reactants are favored, meaning the reaction really hasn't done much, and the acid strength is weak. So one thing I want to point out, again, this is a reaction arrow. And so sometimes you'll see the way that arrow is drawn, you would assume, okay, everything on the starting material side is converted over to the products, 100%. But for equilibrium, sometimes you have arrows like that. And so the meaning of that would be product favored. The meaning of that one would be reactant favored. Again, just keep in mind, it's between the extremes of like nothing happening, like no conversion, and then 100% conversion. You have all of that stuff in between where you get ratios of products to starting materials. And then we translate that into these two scenarios of strong and weak. So as I said, those numbers can be like ginormous or they can be infinitesimal. And that's a little bit hard to deal with, when you're saying like 10 to the 18, like what does that mean practically? So what has been done is this logarithmic function. It's in chemistry, it's abbreviated P. So you apply this P to both sides. So pKa is equal to the negative log of that Ka value. So this negative log, that's what that P means. Now notice in column 3 of that table, sort of the inversion that happens. When you have a large Ka value and you take the negative log of it, the pKa value becomes small. The equilibrium still favors the products and we still call it a strong acid. If you have a small Ka value, take the negative log, you get a large number. that favors the reactants, and it's a weak acid. But fortunately for us, when you shove those numbers in there, you end up with a scale. So that's the pKa scale. And it runs from about -10 to 50. So overall, it's 60 total units. And so we would define a strong acid as lying in between -10 to 0. So that's 10 pKa units. But a weak acid is 0 to 50. So that's much larger, right? The other thing to keep in mind is because it's a log scale, when we're talking about the difference between any two numbers, say that number is n when you subtract them, the actual acidity difference is 10 raised to the power n because we're on the log scale. So as I mentioned, today we're only talking about strong acids. So these lie within -10 to 0 on the pKa scale. Again, chemically that means the reactions, these fully ionize. The table that you've seen is ranked according to pKa. So notice how you start from -14 and we end up at 3.2. So the top of the table here is the strongest. And the bottom of it is the weakest of the strong acids. And something to point out, hydronium, which we talked a lot about today, that has a pKa value of -1.7. So what the table shows you is common strong acids, their molecular formula, their ranking of pKa values, the conjugate base that's formed after you deprotonate them, and then what the name of that base would be. So if we're just interpreting this table and we pick out, say, any two acids, say we pick out sulfuric acid, that has a pKa of -9, we would say that is a stronger acid than nitric acid, which has a pKa of -1.4. So in the last couple minutes here, we'll look at the factors that affect acidity. So we started the lecture off with H2SO4. There's the Lewis structure. We see OH. The H is what we're measuring in terms of the pKa value. But on the prior table, we saw this molecule called trifluoromethane sulfonic acid. And that has a pKa of -14. And so that's the strongest acid that we'll learn in this class. And so, that also has an OH. You can see right there, the sulfuric acid has OH. So why are those pKa values different? So what affects that, again, is the structural features of the rest of the molecule. So if you have water deprotonate that H, so you make that bond, you break this OH bond, you get hydronium, and then you get the conjugate base, which is trifluoromethane sulfonate. So that O is minus, that O is plus. We sort of add those together, it's neutral on the product side. So what about this conjugate base helps stabilize that negative charge and make this really super acidic? There are two main things that affect acidity. That's one, the first is resonance and the second is induction. And we saw a little bit in Module 1 about what resonance was, where we could delocalize a charge, say a negative charge, a plus charge, or a single electron throughout the molecule, and that helps stabilize the resultant species. So with these arrows here, the negative charge on the oxygen, we can form an OS double bond here, break that SO pi bond, and then move the negative charge up to the other oxygen. And then you can repeat that another time. So this arrow is a review here. Again, that's the resonance arrow. And what it's telling you is those three oxygens all share the negative charge. They share the misery a little bit. It's not three separate structures. It's just one structure that all of them are a little bit negative. And because all three oxygens can stabilize that one negative charge, that helps increase the acidity of the acid. So that's a resonance explanation. The other explanation is called induction. And the way that I think about it, and I think the best way to visualize it is induction is like a tug of war, where the bonds are the rope in the tug of war. So highlighted in blue, you see that negative charge. Then you see these blue bonds, these sigma bonds leading to the fluorines. We know fluorine is the most electronegative element. So what the fluorines are doing is, through those bonds, they're helping to pull that negative charge away from oxygen as a means to help stabilizing it as well. And in the four structures shown at the bottom here, to the left was the trifluoromethane sulfonic acid with a pK of -14. To the right, notice those fluorines are now hydrogens. So this is called methane sulfonic acid. Notice that acidity value is -1.2. It's still a strong acid, but it's a lot weaker than -14. If you deprotonate this, you still have resonance stabilization, but really what it's telling you is the influence of those fluorines in increasing the acidity. So as you start substituting H's to fluorines, once you get all three on there, that peps up the acidity quite a bit. And just real quick, I might run a minute over. The last two slides deal with hydrohalic acids, so HX, where X is going to be a halogen. What's weird about these is we know that fluorine's the most electronegative, So you might say, well, HF has to be the most acidic, because when you form the F minus, it's the happiest. But notice the last column here, the trend runs opposite. Hydroiodic acid, HI, is actually the most acidic of that group. And really the reason to rationalize that is if you look at the bond length from hydrogen to that halogen, you see that it increases. And as part of that, because you're going down the column, the atoms are getting bigger, but the proton is staying the same size. So iodine's really big. The protons here, they don't form a really strong bond. So the proton it's almost ionized to begin with. Whereas in HF, they're mostly the same size, so they're closer together. That shorter bond distance means the HF bond is already strong, whereas HI is weak. And if the definition of an acid is to donate a proton, if the bond between that X atom is weak, the proton wants to go away, pretty easily. And so that, is further explained on this slide in terms of like size and van der Waals radii. I apologize for going a minute or two over, but that's the strong acids. Then on Monday, we're going to learn all of the functional groups that lie between 0 and 50 and why they lie, where they do in that region.